Rıfat is a student in the mathematics education in METÜ. It's your fourth year. Okay. And he is doing minor in mathematics also. Okay, we have started to study algebraic number theory, and we focus on the computation of class groups. I want to thank to Rıfat for his hard working and patience. And I want to thank the organizer to meeting us. Okay, we can start, Rıfat.
Before I start, I also would like to thank the organizers and Computation for their contributions. Today we'll talk about the computation of class groups first. Before going into the computation of class groups, I would like to overview some kind of essential points of number field actually. First, what's the number field? I mean, in the algebra, as you know actually, we have fields, and here we actually extend the finite field Q. We actually extend the Q in the finite form. Sorry. Then we call it the finite field. Then here also we define the degree of the finite field. Here we see the number field as the Q vector space and its dimension as the degree. Here, as you see, there are two examples of a number field in different degrees. I would like to go with the discriminant and the basis. As you also most often know, we have elements like W1 to Wn of number field K. Then we define the discriminant of these elements actually, which is equal to the square of the determinant of these elements, and the trace of the determinant of the trace of the intermultiplication of these elements. We'll use it in the following. Again, we have a new term maybe for you, which is an embedding into the complex numbers. I mean, which is basically we embed our number field into the complex numbers. I mean, K. And here, please don't forget that the K has the subfield Q all the times. And here we have a lemma, which is really important for us. And actually, okay, we have some embeddings, but how to determine how they behave, I mean, in different cases. Here we have an element alpha here, which is a algebraic over K. I mean, here then the lemma tells us that we can determine these embeddings. By using the roots of the minimal polynomial nu alpha actually. And so if we have the n roots in complex numbers of this nu alpha, we have n many embeddings, and these are determined by the complete roots of embeddings. Okay, here actually, again, we continue with the embeddings. We say that our sigma k, our embedding is in real numbers. We say that this is a real embedding, and if it's not in real numbers, we call it like a complex embedding. Here, another theorem tells us that if we have our real embeddings and if we have two complex embeddings, we define a new term signature and the R, S. Okay. What's an algebraic integer? I mean, before going into the computation of class groups. And we have an algebraic number first, which is a root of a polynomial of rational numbers. And so that we define algebraic integers also, which is an algebraic number, but here it's a root of a monic polynomial in Zx. I mean, we have a really nice theorem here. I mean, the theorem tells us that if we want to say that this is an algebraic integer, an element is an algebraic integer, then we can look for its minimal polynomial nu alpha. And if it is Zx, it's an algebraic integer. And here you see some examples. And here I would like to define a new term again, ring of integers. I mean, ring of integers is actually intersection of the K number field and all set of ring of integers. And here, all the set of ring of integers, set of algebraic integers is a ring. And because of the intersection of two rings K and O, we say that the ring of integers is also a ring. Here also, I mean, we have an integral basis. It's actually a Z basis for our ring of integers OK. We can write any elements of this ring of integers by using this basis, W1 to Wn, with the integer coefficients. Here, and the lemma tells us that how to determine these integral bases for the quadratic field. I mean, the lemma tells us that if we have a square-free integer d, and if it's not, sorry for the typo, if it's not equivalent to 1 in modulo alpha, then we have integral basis 1 as square root of d, And if we have an equivalence of the form of the first one, then we say that our integral basis is 1 and 1 plus square root of p over 2. And most of the time, we work with the ideals in the algebra and also in algebraic number theory. I mean, here also we have a similar term like a fraction ideal, which has actually the same properties with the ideal. But only difference is that in algebra we say that an ideal is actually must be a subset of a ring. But here it doesn't have to be. I mean, it has to be a subset of the K number field. And also we have a lemma. We can say that every ideal is in ring of integers. Okay, then it has to be a fractional ideal. But we say that a fractional ideal is an ideal if and only if it's contained in the ring of integers. Here also you see some properties of the inverse of the fractional ideal. And another lemma tells us that if we have a prime ideal P, P inverse of P also gives us the ring of integers. I mean, we have a really important theorem to compute the class groups actually. Here we have a Dedekind Kummer Theorem, and it tells us that if we have a principal ideal B of OK, then it has to be a principal ideal. I mean, if and only if it has an element in OK, which norm is equal to B, norm of B. And the Dedekind Kummer Theorem helps us to, I mean, how to factorize the prime ideals into another prime ideal. I mean, here, for example, the theorem tells us that first we have to have an integral basis. Then we have this index. I mean, if our prime number doesn't divide this index, actually, we can compute the nu of theta, which is an algebraic integer. Then we compose it into the polynomials, which are monic and irreducible in z of x. Then we say that we can factorize this prime ideal P into the other prime ideals, but these prime ideals are in this form actually, P and Fi theta. And so that we can factorize the prime ideal in this form. And moreover, also we have the more normal prime ideal Pi, which is equal to P to the degree of Fi, here as we choose, irreducible and monic. Here also, in the picture, you see the logic of the Dedekind Kummer Theorem. Okay, I would like to continue with an example here. For example, we have q and square root of minus 13. So that because of the previous lemma, it's not equivalent to 1 in modulo 4. So that we say that our integral basis is 1 and square root of minus 13. And because of the Dedekind Kummer Theorem, actually, you see that this index is equal to 1. So we can factorize all the prime ideals actually into the other primes. And so that here, I mean, here in this example, I'll look for the prime numbers 2, 3, 5, and 7. Here you see in the table how to factorize them into the other primes. Actually, the most important and maybe the most interesting one is the 7. I mean, the prime ideal 7. Because here, as you see, I mean, we factorized into prime ideal just P7. And so that which is irreducible, and this minimal polynomial is irreducible and monic here in the modulo P. So that we can say that, I mean, we can write the P7 in the form of P comma Fi. Here our Fi is this one, and here our P is this one. And so that we see that this is a principal ideal. Okay, then I would like to continue with the class groups. What's the class group? I mean, first. The class group is defined by the quotient. I mean, maybe I can first say that our fractional ideals consist of our class group. I mean, gives us a abelian group under multiplication. But here the class group is the quotient of the fractional ideals over the principal fractional ideals. And here we define a new term here in class, which is and we say that two ideals has the same class if and only if our ideal A is equal to lambda B for some lambda in number field. And the theorem tells us that the ring of integers is a unique factorization domain if and only if class group is trivial. I mean, we have Minkowski bond, which is really important before computing the class groups. What's the Minkowski bond? As you see here, we defined the degree, the signature, and the discriminant of the ring of integers. And by using and composing them, we get a Minkowski bond, and we will use it. Here we have a theorem. The theorem tells us that if you have a number field of degree and of signature Rs, we say that class group is finite, and class group consists of the prime ideals whose norms are less than this Minkowski bound Ek. And also, you can see that if we define the number of the class groups as Hk, the first property tells us it's finite. Hk is less than infinity. And I mean, here we have a lemma. Maybe you can look for it. Then the lemma actually tells us that, okay, we can factorize the prime ideals into the other prime ideals. But are they, I mean, we choose them in our mind? No. I mean, we also use mathematics here because the theorem tells us that every prime ideal P, I mean, the norm of the every prime ideal P can be written in the form of P to the F for some positive integer F. So that our primes, I mean, our prime numbers must be also less than or equal to Bk. Here you see an example of computing class groups. Yeah, actually, we do the same thing with the Dedekind Kummer Theorem here. I mean, we can we factorize it actually into the prime ideals, for example, for P2. Here, why P2? Because our Minkowski bound is 3, so that we can only factorize the prime ideal 2 into the other primes. So we did this term actually, and here you see that we found the P2, and its norm is also less than the Bk. So it's suitable for us. It's suitable for the computation of class groups. And here we see that actually, maybe in the beginning of the class groups, we said that if we have an ideal B, it is principal. If we have an element in this, ideal whose norm is equal to norm of this prime ideal. And so that we found an element, such an element, actually 3 plus square root of 7, whose norm is 2. And also it's equal to norm of the prime ideal 2. And so that we say that our prime ideal P2 is principal. And we can directly say that the class group is trivial and the number of class groups is 1. Okay, I can continue with the corollary here. I mean, in the previous example, we saw that the class number is equal to 1. But is there any here, I mean, is there something that helps us to directly determine the class group of 1? But what is that? I mean, by using the Minkowski theorem, we found these discriminants actually. And this corollary tells us that these quadratic fields and the imaginary fields, they're also quadratic. They have the class number 1. Okay. Before I finish, I would like to also continue with an example here. Again, we did the same thing as we done in the previous one, so that we computed the degree, signature, and the discriminant of the integral basis. Okay, but here our Minkowski bound is 4.76, so that we can work with the primes 2 and 3 into the prime ideals. Here, as you see in the table, we factorize them into the prime ideals, for example, like the P2 to the square and P2 times P2 prime, P3 times P3 prime. But here, actually, we have a problem. We should look for are they principal or not first. But how can we do that actually? How can we determine it? We have an integral basis, like 1 and a square root of 14, square root of minus 14. So that if we have an element, we said that if an element and whose norm is equal to prime ideal, this prime ideal is principal. But so that every elements are in the form of like 1 times, for example, or a times a plus b times square root of 14. So that we should look for the solution. I mean, we see that they have no solution in the number theory, so that we can directly say that either P2 or P3 are not principal ideals. And here you see that P2 is equal to P2 inverse and P3 is equal to P3. But again, we didn't find anything about the principality ideal. But can we find any relationship between the P2 and the P3? We can look for it. Actually, we have an element here like the 2 plus square root of minus 14. And so that we composed its norm into the prime ideals. I mean, actually 2 times 3 to the 2 or 3 squared. And here, this term, since this term, I mean, is not divisible by 3, we say that we should have only P3 or P3 prime. Okay, assume we chose the P3. so that we factorize this prime ideal, actually, again, these primes, and so that we can easily see that this is a principal ideal, so it has a class group 1, so that P3 times P2 times P3 squared has the class 1, so that we can found these relationships, and we can directly say that our group consists of our group is generated by P3, maybe consists of the powers of the P3, so that we can directly say that our class groups consisted of the cyclic group of order 4. Here are my references, and thank you for listening to me.